Great, thank you very much. Hi, good afternoon. I am Brian Cantrill. I'm the VP of Engineering. I think I'm speaking way too loudly. I'm the VP of Engineering at Joyent, and I'm here to present on our experiences porting KVM to SmartOS. So we have actually ported KVM to another operating system. Of course, the next natural question is, what the hell is SmartOS? SmartOS is an Illumos-derived OS. How many people have heard of Illumos, at least? If you haven't, all right, so not every hand's going up. So I should have had a WTF is Illumos slide as well. Illumos is what has become of OpenSolaris. So Illumos is a true open source fork of OpenSolaris and has been aided enormously by Oracle, wanting to drive employees out of Oracle, sabotaging the operating system, and so on. It's been great for the open source effort, so thank you again, Larry. Illumos is completely independent, and SmartOS is an Illumos derivative. As an Illumos derivative, there's a bunch of key functionality that SmartOS effectively inherits. So how many people have heard of ZFS? Okay, that's great. So a lot of hands went up. ZFS is an enterprise class file system that was originally developed for Solaris. It's since been ported to lots of other systems, including FreeBSD, including the Mac. So a lot of other systems, a lot of really advanced features built into ZFS. And again, it's enterprise grade. And what does enterprise grade mean? Enterprise grade means that we have suffered in the kiln of pain getting the goddamn thing right. And you know that everyone around you in the storage ecosystem is effectively Byzantine in its behavior. It takes a long, long, long time for a storage stack to get right, and that's what we've done with ZFS. We have walked the trail of tears with ZFS. dtrace, I don't know if people have heard of dtrace, as hands-on dtrace, okay, decent number of you. Facility for dynamic ad hoc instrumentation of the system. OS-based virtualization. This is basically, you can think of this as jails on growth hormone if you're familiar with BSD, but it's actually much more than that. This is really OS-based virtualization as a first-class citizen in the operating system operating at hardware speeds, but in a highly contained way, which allows you to drive multi-tenancy very high. And we have network virtualization, this project called Crossbow, which gives us a virtual NIC infrastructure, allows for easy bandwidth management and resource control. So those features are all great, but there's one glaring feature that's missing. We've got a great feature set, but the thing that we were missing was hardware-based virtualization. And now thanks to Intel and AMD, hardware-based virtualization can be now had relatively easier. I wouldn't say it's easy, but it's easier, and with remarkably high performance. And we emphatically believe, we Joyent, I dare say the Illumos community, emphatically believe that the best hypervisor is the operating system. That is to say, anyone attempting to implement a quote-unquote thin hypervisor, I won't name any proprietary names, but we all know who I'm thinking of, anyone who attempts to implement a quote-unquote thin hypervisor will go ahead and repeat 20 years of OS implementation history. And I think that we can all agree that that's actually the wrong path to take. And indeed, we all do agree that this is the wrong path to take. Not only does KVM share this vision, KVM pioneered this vision. And I think it was a huge tribute, Avi, to you and your team that you brought this vision to the world. So not only, of course, did KVM bring the vision, not only did you share the vision with KVM, but KVM itself is best of breed. Highly competitive performance. I love watching the spec numbers and watching KVM is either competitive with proprietary solutions or bidding them, and a community witnessed our conference here with critical mass. So the imperative for us was clear. We had to port KVM to SmartOS. Sounds like a really easy thing to say. Let's just go do it. It's just a port, right? Like an editor. Well, no, not so much. So we wanted to constrain the scope of our port for a little bit. First of all, for business and resourcing reasons, we elected to focus exclusively on Intel VTX with EPT. Full disclosure, Joyent is an Intel-backed company, but it wasn't like Andy Grove was in my office haranguing me to make this decision. Just for practical reasons, we decided to focus on Intel VTX, but we didn't want to do anything that would make AMD SVM support impossible. So we didn't want to screw AMD SVM, but we did want to focus on Intel VTX. Now, one thing is that we are only ever interested in x86-64 host support. Actually, just as I say that, I think actually I should cross out. we are most likely ever interested in x86 64 host support. Atom would be the example where I might be actually interested in x86 host support, but we are essentially only we're willing to do work if we needed to go do x86 support as opposed to x86 64 host support. We are only ever interested in this, I can say emphatically, in x86 and x86 64 guests. Love the Power 7 stuff, and I get a little tear in my eye when I think of RISC, having spent 14 years at Sun, but the reality is that we are only interested in x86 and x86 64 guests. Now, we are willing to diverge from KVM to support Illumos constructs and coding practices, but we really wanted to maintain compatibility with the QEMU KVM interface as much as possible. I think you guys did a great job of getting a really crisp layer in there. I mean, witness the fact, even though I think it's arguably misguided, witness the fact that with the KVM tool is building on top of that interface, building a wholly novel userland. I actually think that that is healthy in as much as it really helps firm up that ABI. So a nice firm ABI there is in everyone's best interest. So, okay, let's get started. Well, KVM, totally rightfully, was not designed to be portable. It shouldn't be designed to be portable. It is specific to Linux. It is specific to Linux facilities. And it became clear to us very quickly, like immediately, like as soon as we popped it up in an editor, that emulating Linux functionality is not going to be sufficient. And that is actually, this is the path that the FreeBSD Summer of Code 2007 effort took, was the emulation of Linux functionality. That won't work for us. The in-kernel functionality is simply too divergent to actually allow that to happen. So that was not going to work. But the flip side is, Avi, just to your remarks this morning, the KVM is stable. And you look at 2634, I mean, you've got a very stable base. It's in production the world over. And we felt confident that we could diverge from the Linux implementation with that 2634 implementation while still being able to contribute patches to the KVM community. And I'll explain why in a second. You haven't seen any patches from us. Hint, it's good news, and consume patches from the KVM community. So we felt that we could do this realistically. Now, it was also clear that just getting something to compile was going to be a significant, if not historic, undertaking, and largely serial. So we would love to have a bunch of folks attack this, but the reality was we just had to start this as something of a small project. Joint engineer Max Brunning, who's in the room. Max, you want to raise your hand? So Max was kind of thrown into the breach there and started on this in the late fall of last year. Now, to expedite compilation, and I'm sure those of you who have done extraordinarily complicated ports will know this, that you can't just go through and get everything to compile and kind of port everything. You got to pick and choose and kind of if-def stuff out. So to expedite just getting the compilation, we took unported blocks of code and we XXX'd them out by enclosing them in if-def XXX. I should have looked it up on the internet to see if I could find the actually historical. I always grew up with if-def XXX, and I'm sure it dates back to the dawn of time. Probably dates back to like the IBM 1401 or something. But anyway, we went with the kind of the nod to history there. If-def XXX code out. Now, once you've got a bunch of XXX code out, how do you know what you want to go pull in? How do you know what code you would be hitting? What we actually did is we took those code sites and we put #else clauses in there that had special dtrace probes with underbar, underbar file, underbar, underbar, and underbar, underbar line, underbar, underbar as the arguments to that SCT probe. Then we can use this nice little D script here to actually tell us what XXX code blocks you have hit and what do we need to go focus on next. And what would often happen is we would go to do something new, the system would fail spectacularly, and we'd say, oh, guess what? We just executed a new XXX that we need to go implement. So this actually happened a lot. Now, Max started in late fall. By late March, good news, Max could launch a virtual machine. Initially, it was only 3 instructions, then could launch a virtual machine that could run forever without panicking. Awesome. The problem is it wasn't doing anything. It was stuck somewhere, God only knows where. It is stuck in the inky black of the BIOS in real mode. Who the hell knows what's going on? But now we were at the point in early April where we could parallelize the effort a little bit. And Robert Mustaki, who's also in the room from Joyent, so Robert and I were able to join Max in April, and we could really parallelize the effort and begin to attack these things. So we quickly added some tooling to understand guest behavior. MDB is our debugger. So we added MDB support. This is both a postmortem and an in situ debugger for both kernel and userland. We added MDB support to map guest PFNs to QEMU VAs. I can't believe this, but we added MDB support for 16-bit disassembly. I swear I would never live to actually be the one doing this, not only doing this, but not at an act of like pedantry, but actually to solve a real honest-to-God problem and to have this thing totally crack the case. When we added MD, these two things together allowed us to actually go disassemble the BIOS, and we could actually see, thanks to the dtrace probes, we could actually see, oh, we're stepping through these 8 instructions, and we had screwed up MMIO. So we had screwed up program IO, I guess, in that case. And we were able to figure out how we'd screwed up program IO and get it back on its feet. And then we also added, and these have been huge, we've just used these all over the place, dtrace probes on VM entry and exit, and in particular, the ability to pull VM state in dtrace with a new VM regs variable. So this allows you to programmatically pull exactly the regs out of the VMCS that you want to debug a particular problem. So we were making progress, and what we would do is we would debug the issue that was blocking us, almost always due to a piece we hadn't pulled in yet. We would go to pull in or hadn't done properly. We would pull in that piece, and we would iterate. Of course, every time I'm making this sound so clinical, every time you're actually scared out of your mind that this is the bug that is actually going to put you out of business. This is the one that is actually you're not going to be able to find. So I don't mean to make this sound too dry. We were terrified for most of this. So just I want to be clear about that. I don't want to have too much machismo here. But we did actually iterate, and some of these were harder, some of these were easier. And we actually think that if you look at the number of XXXs in our KVM port, it kind of tells the tale of the port here. So here you can see Max is struggling to get the damn thing to compile. And XXX is climbing up here. And then, of course, we're pulling some stuff in. Then Max realizes, oh, shit, there's a whole file I haven't pulled in. Got to pull that in. That's all XXX'd out. And we're kind of rumbling along here. I think that is actually what happened there, Max, as I recall. And then we hit April here, and we actually begin to make some progress, and now we're kind of ripping stuff out. And then we're making really good progress actually going and completing the port and pulling actually everything in, cleaning up the XXXs. And indeed, the milestones, you can kind of see the milestones here. We kind of broke through in the daylight here, booting KMDB, which is our in-situ kernel debugger. Once we could boot KMDB, we could actually see the guest's perspective of architecture state. That allowed us to make a lot faster progress. Booted Linux. You know, it's funny, I actually went back and looked at this. I'm like, that could not have been only like 10 days. These were, I actually think, the 10 most terrifying days of my life. That felt like several years. It's amazing to me that I had to go back and quadruple check the dates because this was a particularly brutal problem. A very entertaining self-inflicted wound, which is essentially the story of this port, and I'll get to the actual problem there in a little bit. We booted Windows shortly thereafter. I guess I should have highlighted that we booted Haiku in there. I've become a total fan of Haiku. I don't know what OSs you guys use to actually, when you go to verify a new change, but Haiku does such weird shit to the system. You know, it runs the clock really high, it just does a bunch of weird stuff. And so I love Haiku, man. I think Haiku is awesome. I would say the good news, the reason you haven't gotten any patches from us, and I really actually think this is amazing. I would not have thought this going in. In the course of this port, we did not discover a single bug that you would call a bug in KVM. Remarkably, remarkably solid. We are cynical engineers. So that was surprising, I think, to all of us, and it's a real tribute, Avi, to you and your team and the community. It is a solid, solid, solid piece of code. The only bug that we found that is in KVM or QEMU was a bug in QEMU where it was calling signal instead of sig action on sig IPI. And if we can have the extended lecture on the tortured history of signal versus sig action and why you should never use signal to set signal disposition to anything other than ignore to default. Suffice it to say they weren't, and the semantics on Linux versus Illumos are different there. And it's a very minor bug, but that was it. That's it. The rest of the code, QEMU, KVM, worked. And again, it's a huge tribute to this community and this code base that works as well as it did. I thought you might find some of our self-inflicted wounds. We certainly found them entertaining, so I thought you might find them entertaining. The week that it took us to debug Linux, there were like 6 problems in that week. One of them was, and I highly recommend that you do not attempt this on your own, that we had misconfigured QEMU, we had miscompiled QEMU, such that both QEMU and KVM believed that they were responsible for both the 8254 and the 8259. That doesn't work very well, as it turns out. As it turns out, we actually don't like having the architectural state duplicated in a bunch of different places, and the failure modes, surprisingly enough, are very strange. So that was very painful. This one is in some ways even more entertaining. So in Illumos, we use GS to get to our per CPU state. So we have a per CPU GS base. Linux obviously does not. I'm going to assume you, what's that? It does. Then you've got a bug. Okay, wow, we actually might have a bug. Okay, then if you got per CPU, if you got a per CPU GS base, then we actually do have a patch for you. Oh my God, I feel so happy. Because the GS base is not properly restored on some thread migrations. So there are some cases when you do a thread migration, and maybe it's impossible, maybe you can't hit it in Linux for whatever reason, but we were able to hit it when we poured a bunch of load on the system for a while. We could actually hit this. So the manifestation of this was terrific, and I've been doing kernel implementation for 15 years, and I've not actually had this particular failure mode. I've said that a lot, of course, but this particular failure mode was a new one. I had 2 different CPUs, one of which believed that it was the other from a software perspective. Oh my God, the mayhem, because you honestly, you don't know, I mean, just Linux does this as well, you get to that per CPU state, tells you what thread you are, tells you who you are. Well, you think you're someone else, but you're not someone else, you're you. Like you're just wrong on that perception. And so you go and you die on the most fucked up assertions of like, wait a minute, what am I doing here? I'm over there. It's like, no, you're not over there, you're over, what the hell is going on? And it took us a long time, and actually this is one, we've had a lot of these bugs over the years. I honestly don't know how we would have cracked this without dtrace. We were using dtrace, and in particular dtrace has the ability to do post-mortem instrumentation, where you can have a dtrace enabling, and then when the system dies, bring it up, have the crash dump come back up, and then actually go through the dtrace output. And so that was key for cracking this one. The other one, another self-inflicted wound, and this is a good lesson to us in terms of being cautious when we go re-implement functionality in KVM in terms of the Illumos equivalents. So the FPU save routine, there was an FPU save routine that was in KVM, or actually in Linux, and we dropped that in to our KVM. Well, we've got another one in Illumos, so we might as well make the call out to it. So we replaced that with a call to save the FPU registers. Well, that call actually is slightly different than just an FX save. It has an FX save, and it also clears TS and CR0. TS is the bit in CR0 that indicates a task switch, and that's what you are going to get an NM, you're going to get a pound NM when you access floating point state. We use that pound NM, like I imagine you guys do, a lot of operating systems do, we use that pound NM to restore your FPU state. Well, if you don't hit that pound NM, you will go flying past your first use of FPU registers, and you'll just start using whatever's there. It's like, it's got nothing to do with your registers. It's like, well, how often do you use FPU? Well, there's this little thing called memcopy. It comes up a lot. It turns out if you call it memcopy, you're using the floating point registers to stage in memory, and just wild, exciting things happen. This is like, we're doing a full build in a KVM guest, and there's a corrupt object file. And you're just like, okay, where is the kernel developer suicide hotline? Because I actually need to call it right now, and I need to be talked off the roof. But fortunately, we gritted that one out and nailed it. In terms of performance, not surprisingly, although there's an asterisk there as well, our port, when you look at just pure CPU, and this is a sysbench CPU running, runs same speed as bare metal, same speed as Linux KVM, same speed as SmartOS KVM. So that was very vindicating. It actually took us a surprising amount of time to get to this result, because when we first did this, and this was dead reproducible, SmartOS KVM was 5% faster. Now, and those of you who've done benchmarking know that this is how tough benchmarking is. Because, hey, you're 5% faster, hey, go home. It's like, hey, you're 5% faster. It's like, no, that doesn't make sense. Like, you can be awesome, but honestly, like, we're all talking to the same hardware here. We can't be 5% faster. And these are the exact same CPUs. They are the exact same motherboards, exact same DRAM, going down every single thing, same. And finally, Brendan Gregg on the Joyent team finally cracked the code on this. We were seeing dynamic overclocking, right? So the Intel's Turbo Boost functionality in the Nehalem is something to be very careful of whenever you're benchmarking. Definitely turn that sucker off, because what that'll do is, based on ambient temp and so on, that'll overclock you up. Now, your TSC frequency is the same. So the only way to determine your true CPU frequency, I think there actually are some ACPI regs where you can get the actual true CPU frequency, but needless to say, you're going to end up being very confused when you go to compare results. So I would love to tell you that we're 5% faster, but we're not. So when we went to turn that off, everyone was the same speed, which was a relief. So, And in terms of, we did and we're still in the kind of early stages of doing the benchmarking here, and I should just say that the point of our benchmarking efforts was to make sure that we hadn't fucked anything up, because we had plenty of self-inflicted wounds along the way, every reason to believe we would have some more, so we just want to make sure that we were in the hunt. And so this is a sysbench MySQL benchmark. You can see the bare metal performance is there, and here are Linux KVM and SmartOS KVM at essentially the same performance here. There's kind of this interesting gap here. We would want to understand that due to CPU scheduling perhaps. I don't know why there's that crossing there. I mean, the numbers are reasonably reproducible, but we view these as kind of basically statistically being essentially the same thing, which is good. We're delivering the same performance that you're delivering, and you guys are delivering. KVM is delivering great performance. So in terms of the port status, it's publicly available. There's a GitHub repo for KVM itself. We've got a branch of QEMU 0.14.1, very slightly different. I'm going to talk about those differences in a second here. And within its scope, in terms of the way we have kind of defined the scope of this project, this port for us is at or near production quality. If you have AMD SVM, it is not at or near production quality because there is no support for AMD SVM. So it depends on what you're doing. But for us, this port, we do believe that we are approaching rapidly production quality if we're not there already. Actually, very funny this morning. So we just released this morning, and not 45 minutes after we released it, another distro of Illumos, Open Indiana, picked this thing up on latest bits and actually booted a guest, Windows 7, that we actually hadn't booted yet, and posted the screenshot of Windows 7 booting, and major sigh of relief. It's like, boy, that could have gone the other way. We booted Windows 2008 R2, we booted various Windows variants, but not actually gotten to Windows 7, and we all know that anything can go wrong, so that was a relief. But this is definitely usable as it is today. So I want to actually go through some of the limitations of our port, some of the things that we have not done, some of the things that we don't intend to do. I want to go through some of the divergences where we implemented things in a slightly different way or used a different facility. Those are just more for your curiosity. And then some enhancements, some ways that we think that we're actually doing some really interesting things with KVM that we're really excited about. So limitation number one, this is an important one, is guest memory is locked down. So we are biased by the fact that we are a cloud provider. So we actually have thousands of machines, tens of thousands of customers. We've been doing this for a long time. And for us, memory oversell is not worth it. Memory oversell, it works great for idle workloads, but when you have a bunch of folks that are actually going to kick the snot out of the boxes, the actual variable latency that you get from memory oversell just does not pay for itself in terms of the marginal revenue. So it is a business decision at Joyent, and perhaps something of an opinion, albeit one that is grounded in fact, that we do not believe in memory oversell. So we currently lock down guest memory, and failure to lock down memory will result in failure to start. This is a resolvable problem. We're just not hugely interested in resolving it because we're not interested in memory oversell. We think that someone in the community probably will be interested in it, and we would love to help them out, but we're probably not going to drive this ourselves. In part because when you are talking about high multi-tenancy environments, we do believe that the hardware is actually the wrong level to virtualize. Hardware virtualization is great, and we love it, and it's great when you want to run all these different guests and so on, but when it's time to actually crank the multi-tenancy, when you run one platform as a service and get up the stack, actual OS level virtualization is a much lighter way to virtualize. You've got a single operating system kernel. You can punch out these zones, and we run production loads with 400 tenants per machine on a 2U machine. 2U machine, 96 gigs of memory, has got 400 tenants on it, each with what feels like a virtual operating system running at very high performance. You can't do that with hardware virtualization. You just can't. It doesn't matter how great you are. So that's another reason why this is not hugely interesting for us. We also don't have any memory dedupe or kernel same page mapping in Linux parlance. It's technically possible. We don't see an acute need. Maybe we will see an acute need, in part because of the same reason we lock down guest memory. Definitely interested to hear experiences about this. I mean, we heard in an earlier talk that this is being used broadly. We would love to know what kind of memory savings do people see? Or is there one kind of guest that sees more? I think it is kind of my inference from lore. Yes, Avi.
So Windows does a lot of zeroing of free memory, and it doesn't use all of its memory for cache. So if you have Windows XP, it will collapse all of those 0 pages into just one page. And of course, all of the shared text will be collapsed.
Sure.
You can see a significant saving. If you run virtualized desktops, then usually they're running the same similar workloads, the same Office suite, the same kernel, so all of those can be collapsed, and of course all those 0 pages.
Right, interesting. So yeah, I would be very, and the Windows XP data point is a very interesting one. I would just be curious about what the rate is there. Is that a 25% saving? Do you get a 25% bump? Do you get a 50% bump? Do you get a, do you get a 3x bump in your, what is it, how much is your memory reach?
I don't recall the exact numbers, but we saw very high here.
Significant, yeah. And I think, we'll definitely, this is not something that we're close to having implemented. And this would be an Illumos thing. I mean, just the way it was in Linux, this would be a generic thing, effectively. Another question that we would have is kind of what was the performance overhead from page scanning. That's an important question for us. We don't support nested virtualization currently. We're not sure that we're ever going to implement it. It's hard, especially on VTX and VMX. It's just ugly, and I mean SVM. It's a little more elegant. We would love it for our own development purposes. And VMware, if you want to, despite all of my kind of throwing you under the bus, if you'd like to implement it in VMware Fusion, that would be awesome. We would love to see nested virtualization because we would use it ourselves for development, of course. But we don't see the acute need for ourselves. Again, interested here in experiences with this. Is it being used in production, or is this primarily for development? I mean, I don't know. I'd be in. Feel free to.
It's currently a solution looking for a problem, and
that's that you've told me all I ever need to hear.
It's like a solution that is a problem because it's incredibly difficult to support. The code is incredibly complicated.
Yeah, we went through the patches, and it's like, wow, that is really nasty, and nasty because the hardware does not helping you out. I have to say.
When you think through it, you get your mind in a deadlock very soon. It's horrible.
Interesting. Those are very helpful data points.
I don't know if anyone using it for production, but we're certainly using it for development.
Sure, of course. I mean, for development, it makes a ton of sense. But for development, it also makes a ton of sense for someone else to go implement, right?
Not virtualization development, but actually application stack development on top of virtualization.
Right. Sure, of course. Yeah, that's what you're saying. Yep, and that's interesting. I'll be interested to hear if that goes into production, or to what degree those become production loads. One divergence. We really want to minimize the patches load on top of QEMU. We don't have an anon inode get FD equivalent, so there is not a way to actually open a new FD from within a driver's IOCL routine effectively, which is what you guys are doing here. You guys do this to implement the model of a one-to-one mapping between a file script and a vCPU. We actually experimented with, well, let's just break that mapping and have the vCPU be a parameter every octal. It's like, oh, we've completely diverged. Okay, never mind. Unwind. Let's add a new KVM clone ioctal, one new ioctal that makes the driver state and the operated upon instance point to effectively another. And then to create a vCPU, we've got slightly more complicated code in QEMU. It's like 10 lines of code that reopens dev, does a fresh open of the KVM, calls KVM clone on the new instance, specifying the old one, and then is able to go create a vCPU on it. We've got all the errors in there that you can't create multiple vCPUs on a single instance and so on. So that has worked out very well for us with the caveat that we got a small amount of if-defery in QEMU, which obviously we'd like to avoid, but we can't in this case. One very minor divergence, we've got something called context ops in Illumos. Actually, these were originally implemented, kind of interesting historical detail, for CPU performance counter virtualization. I don't know if you guys do the same thing, but we virtualize CPU performance counters and have for many, many years, in part because we were trying to understand a microprocessor that was enormously non-competitive, which was Spark, so we really needed every bit we could get. We implemented these context ops, and we actually used them to great effect in KVM. Where we perform the equivalent of a KVM sched in, KVM sched out. So you get code that can be called as you're being taken off CPU. So that was, if we didn't have that, we would have had to implement it, which would have been rocky. For timers, Illumos has got an arbitrary resolution interval timer facility that I implemented way back in the day, in the late 90s. It's called the cyclic subsystem. Cyclics can be bound to a CPU or processor set. They can be configured to fire different interrupt levels. And originally, this was designed to be a high-resolution interval facility, and indeed, the system clock itself is implemented in terms of it. But over the years, we've actually made some enhancements to it, and they can now be dynamically reprogrammable as one-shots. So all KVM timers are implemented as cyclics. One slight difference: we don't migrate cyclics when a vCPU migrates from one CPU to another. Instead, we actually just do we poke the target CPU from the cyclic handler. So very minor divergence. In terms of enhancements, I kind of threw this up there because I know we believe this is an acute problem in KVM and in the broader world. We actually didn't do anything to ZFS. ZFS just works with KVM. So you take a ZFS, create a ZVol, and have QEMU and KVM just go to town on it. So that just works, but by using ZFS, you get a couple of enhancements. For one, you can stop the experiment of the user-level file system in KCOW2, which was tough to sit through. It's very earnest work, and I don't mean anything against the presenters. So the presence of ZFS allows us to do a lot of things. It allows for constant time cloning, which we've used a lot as we've been just testing this stuff. It's great to be able to just clone an instance and be able to go. You can clone it while it's up, no problem. We've got a unified adaptive replacement cache, the ARC, that allows for guest I/O to be efficiently cached in the host. And that allows us, we want to actually use the DRAM that way because it allows potentially massive performance improvements in random I/O. Of course, it depends on locality. And we believe that the ZFS remote replication facility can provide a really efficient foundation to do cloning and migration in the WAN. So that's part of where we're going to be taking this. In terms of, we also support OS virtualization. Our implementation does not require to run an OS virtualized instance, but we chose to for our implementation at Joyent. And the reason we did that is actually because we use it as a mechanism for accounting. We use it as the basis for quality of service, resource management, I/O throttling, billing instrumentation, et cetera. So that is the reason we actually run the QEMU process in a zone. It's the only process running in a zone. But then all these KVM vulnerabilities came out at the Black Hat conference, and which became very interesting to us because if you break out of, and I thought it was actually very interesting, and again, obviously a tribute to you and this team, this community, the vulnerabilities were not in KVM, right? The vulnerability, you know, it was pitched as a KVM vulnerability. It's a QEMU vulnerability. You're breaking out in the QEMU. Well, if you break out in the QEMU, if you somehow burrow out in the QEMU in our implementation, you just find yourself having burrowed out into a much larger, much more secure prison, which is a container. So you can't actually do anything. In fact, you actually have less privileges there than you do in a normal container. So we think that the OS virtualization really neatly containerizes QEMU and drastically reduces the attack surface there. We've got deep support for network virtualization. We create a virtual NIC per KVM guest. And we wrote some simple glue to connect this to VirtIO. And you know, we just wanted to satisfy ourselves that we could push 1 gigabit to and from a KVM guest. We were able to do that, so we kind of went on to do other things. So we know it performs at least adequately, but I'm sure there's lots we can go do there. VNICs give us a ton of things that are, I would say, possible with IP tables and EB tables and so on, but much, much, much easier. You just create a VNIC and you assign it to the QEMU instance. You get anti-spoofing, for example. Anti-spoofing just kind of comes along for the ride. You indicate on the VNIC which MACs this thing is allowed to have, and no one can pump up an interface that doesn't have that MAC. It gives you flow management, so you can actually share a 10 gigabit interface and actually chunk that up among 10 different guests and assure that no one can actually drown it. Or if you are, actually this becomes really critical if you are in certain parts of the developing world where bandwidth is at a premium, you really need to confine bandwidth from a particular guest. That allows us to do it very easily. We also get nice resource management, observability into a per VNIC and thus per guest throughput from the host. That nicely comes along for the ride. Illumos has a KStat facility for kernel statistics. We took the KVM vCPU stat structure, we implemented that as a KStat, and then we added a KVM stat tool to Illumos that's been pushed. That's upstream now, that consumes the KStats and displays them per second and per vCPU. So we use this all the time when we're looking at performance. So what we do, this is, for example, this is 1 second of KVM stat output. This is a Linux, there's a 2 vCPU Linux instance here that's idle, and a 4 vCPU SmartOS instance that's actually in the middle of booting. So you can see, and you guys recognize all of these. These are the things that you added that we've effectively exported up. One just side note here, this can drive you nuts. We were seeing that when a machine first booted, it would take 1,300 exits per second. And then as we were debugging it, it would go away. And then what the hell? We'd go reboot the instance, and then it would come back, 1,300 exits per second. And we're debugging and debugging and debugging, it would go away. And finally, Josh Wilsden, who's a Joyent engineer in the room, Josh is like, wait a minute, I wonder if this is due to the screen blanking. And sure enough, it's that 5-minute timeout. Before the screen blanks, it's doing, and we were seeing a bunch of EPT violations as it was writing to video memory, presumably. So kind of entertaining, but a very good way of seeing this across many, many, many vCPUs and VMs. In terms of dtrace, I think it's kind of ironic. QEMU 0.14 has dtrace probes, even though it's never actually worked with dtrace, because to actually support system tap, which is kind of funny. So we actually lit those suckers up, and those all lit up great. Then we added a whole bunch of SCT probes at KVM itself. All the call sites of the trace underbar routines became SCT probes. Gives them 0 probe effect when they're disabled. We added the VM regs registers I mentioned, and that allows you to dynamically, safely aggregate instrument on an arbitrary basis per vCPU, KVM and so on, and it's very nice to use this with KVM stat to understand workloads. So for example, here's a very simple dscript that looks at guest exit and aggregates by process ID, thread ID, and the actual exit reason. And then once a second kind of prints this thing out as a nice report. We were running this fork exec exit workload. Maybe this is probably not news to anybody, but so when you start a Linux process, it executes CPU ID 3 times in userland. Maybe that's faster than, maybe there's no other way to do it. I was surprised by that, so I wouldn't, we only discovered this a day or two ago, and I would love to hear I'm sure there's a story there. So anyway, we see high exits. We're seeing 8,000 exits per second running this workload that just forks and exits, which was kind of interesting. I'll just got a couple more slides to wrap up here. Totally orthogonal to this work, but complementary to it, we developed a real-time analytics framework that instruments the cloud using dtrace and visualizes the results. And then we've been extending this facility into the new dtrace probes that we built into KVM. And we've only been experimenting with it, and only very recently, but the results have been really interesting. So here is ext3 write offset. So this is time on the x-axis. This is offset on the actual logical volume on the y-axis. And this is a workload that is writing 3 gigs over and over again. It's writing 3 gigs, deleting it, writing 3 gigs. And so you can see dunk, 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 as it writes up the platter, which is good. I mean, this is, ext3 is doing what we would want it to do. But this is interesting that from the kind of the bottom looking up, we can actually infer things about the guest and understand perhaps a little bit of what the guest is doing. Here's one that's really wild. So we had this interesting idea. Well, we can't tell you what process is running, but we know what CR3 looks like. And we know that CR3 has a pretty strong correlation. CR3 is your MMU context. CR3 has a pretty strong correlation to process. I don't know what it's called, but I know it's hex value. So what we can actually go do is watch thread or process scheduling. And this is a single vCPU instance. This is running 2 compute-bound workloads. We're idle here, and then we start writing these workloads, and you can see the Linux scheduler trading these things off, just as you would expect. So, wow, this is interesting. Let's amp it up. So now at 999 hertz, and let's take one of those compute-bound processes and re-nice it. And you can see that this guy basically falls off and just kind of appears every once in a while. And then we kind of flip it around. You've been on too long. OK, you get off, and now we're going to run this other guy. And we get to see interesting stair-step pattern. I'm sure there's something. I'm sure there's not a doctoral thesis, but maybe a master's thesis, probably an undergraduate thesis, waiting to be written on what's going on there. Same view, same sample frequency, but now horsing around at different nice values and seeing all sorts of crazy things. Things that you would expect, right? And so, by the way, I should have made this clear what we're seeing here. What we are seeing is the time on the x-axis and the offset in the second on the y-axis that's sampled. So what you are effectively seeing, if you were to take every strip and flip it 90 degrees and line them all up end to end, you would have the Linux scheduling behavior. I ran yellow, I ran blue, I ran yellow, I ran blue, I ran yellow, I ran blue, and so on. We don't know what. Yellow is the process named 0x67D8000, not terribly useful, but at least gives you insight that you might not have had otherwise. Here's a wild one. This is the last one I got here. This is IRQ requests, again, broken down by sub-second offset and vector. We know what IRQs were dropping on you. Let's go look at those. And here we can see that there's very clearly some time-related vectors here. These are time vectors here. And so when you're seeing these stridations, you've got something that's very time-based. You can see some of these diagonals that are probably time-based but relative instead of absolute. And then you have these kind of free-for-alls here where you have a bunch of interrupts smeared all across the second. So again, interesting. Not sure if you can do anything with this, but interesting to stare at nonetheless. In terms of engaging the community, we're very excited to engage the KVM community. A couple of 3 concrete things we would love to work with the community on. One is just working on KVM performance. With dtrace, we have much better visibility into guest behavior. And to us, it seems pretty likely that wins in, our KVM implementations have got so much in common that wins in one are probably going to be wins in another. So let's work together and let's go kick the snot out of our proprietary hypervisors by understanding KVM better and better and better on arbitrary guests in production. So that's something we would really like to work with you guys on. We'd also like to collaborate on testing. We dream, and perhaps this exists, perhaps this dream is already a reality, of a farm of oddball ISOs, in particular OS2. A buddy of mine from school was one of the very early guys at VMware, and he always told me that OS2, once they could boot OS2, they could ship. because OS2 was so fucked up in every single thing it did. So I would love to have an OS2 ISO. I mean, I figure if we boot OS2, we are done. So that would be great. We would also like to collaborate on benchmarking. I haven't taken apart SpecVert SE 2010. Spec and I have a long and complicated history with one another. It's like a girlfriend with whom I had a violent breakup. So that said, it's great to see we have this new spec benchmark, and I would like to understand it. I'd like to understand your perspective on it. Hopefully you guys are involved in that. And we would like to work with the community to develop some standard benchmarks. This is actually a lower priority for us. I kind of don't care about that as much. I really care about these first two things quite a bit. Just in terms of thank yous, Josh Wilson and Rob Golwich from Joyent are in the room. They were instrumental in this. Brendan and Greg for all the performance work on the overclocking. Fabrice Villard, of course, I feel is like the kind of the unspoken spirit in the room for lighting the path with Kimu. Intel for a ripping fast CPU along with EPT. Ave, you and your team for putting it all together with KVM, and of course the Illumos community for their enthusiastic support. So thank you very much.